Hello there, Mr. Sutton bringing you this lesson on exponential growth and decay. In this one, we're going to solve real-life problems involving exponential growth and decay. For your warm-up, see if you can express the following as a differential equation. Over time, a positive quantity y grows at a rate proportional to itself. All right, let's see how you did with that. So we're saying that the rate of change of y, dy dt, is equal to, well, the quantity times some k value. If it's growing at a rate proportional to itself, that means that the derivative is just going to be y itself times some constant. So here's how we can express that. And then go ahead and see if you can find the general solution to this differential equation. So to do this, we need to do some separation of variables. We don't see any t's out here, but we can at least divide both sides by y to get that with the dy. And then this dt, let's put it over here on the right side to go with the k. Taking the antiderivative, that's going to be ln of y equals kt plus c. Now you might be wondering, hold on a sec, don't we have an absolute value in the ln? Well, I did say y was a positive quantity, so we've already taken care of that before we even started. To get y by itself then, we have to raise e to both sides. So we have y equals e to the kt plus c. And we could actually go a little bit further. So when I'm adding exponents together, I could really think of this as e to the kt times e to the c power. Now, we're going to fudge this a little bit. E to the c power, c is a constant, e is a constant, so e to the c is just one big constant. I'm just going to call that big C and stick it out in front of my e to the kt. So this c isn't really necessarily the same constant as this c here, but it is a constant, and that's all we really care about at this point. Now here's the other thing we kind of care about. What kind of growth is this if you have a constant times e to some power? Oh yeah, that's exponential growth. I mean, it's the title of the lesson, but still, it's a revelation, isn't it? So this might remind you of a formula you saw in pre-calculus. This was your continuous compounding formula, the PERT formula. In that formula, P was your starting amount. Same thing over here, except we're calling it C. C is your initial amount. It's the y value when x equals 0. In the old days, R was your growth rate. Now it's going to be K. And then T is still time. That hasn't changed. So, based on what we just learned, let's try the following problem. During the exponential phase, E. coli bacteria in a culture increase in a number at a rate proportional to the current population. If the growth rate is 3.2% and the current population is 199.0 million, what will the population be 9.9 minutes from now? Okay, a lot of reading here. The key word here is that this is increasing at a rate proportional to the current population. So you might be wondering, if this is a lesson about exponential growth, why is it happening at the calculus level? Didn't we already do this at the pre-calculus level and possibly even earlier? So we've kind of just dressed this up in calculus lingo. This whole growing at a rate proportional to the current population, at this point, you need to recognize that that is exponential growth. They did mention exponential up here as well. So we don't actually have to set up a differential equation like we did on the last page. If you recognize that you have exponential growth, you can actually go straight to your exponential growth equation, y equals ce to the kt, and skip that whole differential dance. So go ahead and solve the problem based off of that. All right, let's see what we got here. So we've got a c value we need to plug in. That's going to be the current population of 199.0. E is just E. What's our K value? Well, again, that's our growth rate, so that's going to be 0.032. And then for time, we've got 9.9 minutes. So we just have to plug all of that in together and use our calculator. So here we go, plugging it all in. And that comes out to 273.173. And that'll be million bacteria. Now, just as a follow-up question to this, how could we find the population if they asked for it 9.9 minutes ago? Give that a thought. So how do we do that? If we're going back in time, we need a negative time. So you can go back in time if you just make the t-value negative. Here's another problem. Read this one and then see if you can figure out how to get started. All right, let's see how this went here. So this is kind of a weird problem because we've got atmospheric pressure and we're decreasing approximately exponentially. So that's already different from the last problem where things were growing. And here we're asking at what elevation is the pressure 1/2 of the pressure at sea level. So we have elevation is kind of an input and atmospheric pressure is kind of an output. Elevation in this problem is basically taking the place of time. Pressure is a function of elevation here. And we've also got exponential decay. So we're going to need a different formula for this one, slightly different. This is going to be CE to the negative KT. So now this is what we're going to be plugging things into. What's our initial value? Well, we don't actually know. We have a target value. We want to know at what elevation is the pressure 1/2 of the pressure at sea level. So instead of writing y here, we can write 1/2 c. We don't know what c is, but at least we have some kind of relationship between them. How about the k value? Well, we have 12.5% decrease, so that's going to be negative 0.125. And then for the t value, that's actually what we're trying to find here. We're trying to find the elevation, and elevation we're representing as t. We could have represented it with an e, but then wait, we have a constant named e, and that would be confusing. So we'll have to just kind of grit through it with a t. So plugging all that in, we can divide both sides by c. Do you know where to go from here? Oh yeah, if I want to get rid of e, if I want to get an exponent out of exponent land, I need to take the log of both sides. ln would be the best one. So we can write ln of 1/2 equals negative 0.125t. And then let's just divide to figure out t. So taking the ln and dividing, I'm going to end up with 5.545. And what's my units on this? Well, we were looking for the elevation, so that's going to be kilometers. Here's our last exponential problem example. Pause the video and take a moment to read this and see how far you can get on this one. All right, so this one is a little bit weird because they're eventually asking for in how many years the population will reach a certain number. So they're asking a how long, but they're also giving us a time in the problem. The only thing that we can really be sure about to start this thing is we're talking about exponential growth because the population grows at a rate proportional. So we're going to start with y equals CE to the KT for this one. It's definitely growth, so positive K. But now where do we go from here? We eventually want to know the t value because we want to know in how many years. And we have this target value of 1,574 that eventually has to get plugged in for y. And we also have, let's see, a current population of 1,141. So that's going to be our c value. But they didn't give us the k value, and we kind of need that if we're going to solve for t with all that other stuff. So in order to find that k value, we're actually going to use this other piece they gave us. They said if the population was 785 7.8 years ago. So they're giving us a value of the function at a certain time. We're going to use that along with this initial value to figure out k. So let's say that we plug in 7.8 for this function. So that's going in for t. The initial population, the current population, is still going to be 1141. That's going to be the c value throughout this problem. But initially, our target value for y is this 785. So we're going to write 785 equals 1141 e to the negative 7.8k. Negative because this is 7.8 years ago. So we're going back in time for this one. With all this information plugged in now, we have enough information to solve for k. To start this process, we need to divide both sides by this coefficient here. So we've got 785 over 1141. And now what? Well, we need to get k out of the exponent. To do that, I can take the ln of both sides. So I've got ln of this fraction over here on the left, and ln just cancels out the e, so we just have negative 7.8k on the right side. And now I'm just going to divide by negative 7.8, and that'll give me my k value. Let's do that on the calculator now. So I've got ln, fancy fraction, 784, 1141, and then my value there, my back in time value, enter. Comes out to about 0.0479 and some change. Now, normally I would just say round this off to 4 decimals because that's usually enough to get your 3 decimals of accuracy for these. But on exponential problems, it is not enough. These functions can grow so quickly that even a decimal further out can make a huge difference on these. So my recommendation on these would be to not round off on the middle steps. Instead, store and use these weird decimal values on your calculator. So I'm going to say k equals a, which I'm going to say is approximately that stuff that we just talked about on the calculator. But instead of actually using 0.0479 elsewhere in the problem, now that I've got this in my calculator, I'm going to store that value as whatever you want. I'm going to do alpha a, but really the letter doesn't really matter here. So now I'm going to keep using that, the exact value that the calculator gave me. All right, moving on. We got our k value, which I'm going to call a from now on in this problem because we've defined it now. Now I just need to find the t value. So if you didn't get this far, pause the video and see if you can finish this one off. All right, so going back to our original formula, we now have a target value of 1574. That's ultimately what we wanted the population to grow to. Still have that initial c value of 1141, and now we have e times at because now we actually figured out what k is. So moving on then, we just have to rearrange this and solve for t. Pretty much the same steps that we did to solve for k over here. Divide by the 1141. Take the ln of both sides to get rid of the e. So we have ln of all this stuff equals just at. And now we can divide by a, this decimal over here, to get our final answer. Calculator time. So now I've got ln of all that stuff divided by a, which I stored this value in. And that's going to come out to 6.709 and some change. So I'll call that 6.710 to round it off to 3 decimals. And that's going to be years because we were solving for time in years. So that's it for this one. Hopefully you are feeling exponentially better about this material now. Until next time, Mr. Sutton signing off.